So this video lesson is going to be all about creating stem and leaf plots. In order to consider that, I want to take a look at this set of data. The number of apples on apple trees in an orchard. And I want you to consider how could we represent this data visually so that anybody could understand it as long as they knew how to interpret what we wrote down. And first, we need to notice that there are a lot of data points here. There are 6 in every column, and there are 3 columns, so that means there are 18 data points amongst all of these apple trees here. 18 apple trees that we found out the number of apples on them. And so starting with the idea that maybe we could use a bar and line graph like we looked at the last video lesson, we can see that there really are a whole lot of data points here, and it'd be a very crowded bar and line graph. And there's nothing to say over time either, so maybe a line graph really isn't the type of representation that we're looking for. And so without either of those two, it could be tough to figure out what it is that we want to do and how it is that we want to represent it. But I want to look a little bit closer at the apple tree itself, and we're going to use these branches to try to help us figure out what we can do. And now if you look at a branch on an apple tree, you notice that we have one singular branch that goes off of the main trunk of the tree, or rather we have limbs that split into branches, etc. But off of one branch, any one of those branches, there could potentially be many apples coming off that branch. And so using the apple tree, we could consider a way where we sort this data into small sections, maybe like the branches themselves, and organize the data based on what things are related to each other. And so in order to do that, I want to look at these data points based on what is their tens digit. Because if we look at these apple trees and these apples based on based on what their tens digit is, then we can start to consider what things are similar, what are different, how is it organized, etc. Well, we only have one data point that doesn't have a tens digit, and that's an 8. If we look at the ones that have a 1 as their tens digit, we have a few of those. Not quite as many as we had in, or not quite as many as we have in, say, the 2's digit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different data points that have a 2 as their tens digit, 2 that have 3, and finally just 1 that has a 5. We'll make that yellow also. So we have these data points that break down with some certain tens digits. Now if we organize them by tens digits and sort of created a table and said, well, which data points do we have that work with our certain tens digits? And I'm going to organize it like this. We have a 0, 1, 2, 3. I'm going to include 4. We don't have 4s here, but 4 is a possible tens digit, so I'm going to put it there because I want to be complete and have all possibilities here. Well, for 0 tens digits, the only thing we have is an 8. For our ones digits, we have 7, 8, 8, and 9 because we have 17, 18, 18, and 19. So let's write those all separately, 17, 18, 18, and 19. That way we can see there's a 17, an 18, an 18, and a 19. And this already is starting to look a little bit better than just writing all of these representations as a list of numbers. Certainly better than a crowded bar graph that would be tough to see exactly what's going on. Now we get to the 2's. We have a lot of digits that are in the 20s. And I want to organize them from least to greatest too, because that way we can see exactly how many of each we have and sort of how the data is patterned. So we have a 20. We have 2 21s. We have 1, 2, 3, 4 24s. 1, 2, 3, 4 24s. We have a 25 and a 29. For 3's, we have a 30 and a 31. We have nothing in the 40s, but I'm going to include the 40s there because I feel like if we have a 0 tens digit, 1's, 2's, 3's, and then jump to 5s, we should include the 4s there to make sure that it's complete, and we have a 51. And so what we've created here is a table that shows all of the numbers of apples on the different apple trees, but we do it by organizing it by tens digit. And how is this similar to a branch on an apple tree? Well, if we consider these numbers like the branches and these numbers like the apples, then each branch has one or more, or maybe 0 apples coming off of that branch. So the 0 branch has an 8, the 1 branch has the 17, 18, 18, 19, the 2 branch has 20, 21, 21, 24, 24, etc., etc. And this is actually what we call a stem and leaf plot. The numbers here that we thought as apple tree branches are called stems, and these numbers here are called leaves. As you can see, many leaves come from one stem, just like many apples can come from one branch. So go ahead and pause the video here and write down this definition of a stem and leaf plot. A stem and leaf plot displays data in increasing order, breaks down data points based on similar place values, which are the stems, and then orders the places that remain, and we call them the leaves. So go ahead and write this down, and we'll look at another example of creating a stem and leaf plot here in a minute. So let's look at one more example of creating a stem and leaf plot, and then I'll give you an example that you can work off on your own. So this is the speed of animals at their fastest. We have elks, cheetahs, greyhounds, etc. You can read the animals over on the left, and we want to create a stem and leaf plot based on this data. Well, if we looked at it before, if we look at it the same way as we look at the apple trees and apples, we'd consider what place values perhaps can we order these numbers by that make them similar. And these are all numbers in the tens, less than 100, more than 10, so they all have 2 place values. So let's look at place values starting with the tens. Our stems are going to be the tens place value. We have some 3s, we have some 4s, we have some 5s. We don't have any 6s, but I'm going to include them because it's important with a stem and leaf plot to include all of the different possible stems. Even if there is nothing in the stem, we need to include every stem in order. 6 is a possible stem, even though we don't have a 6 as an actual stem in this data set. So with our 3s, we have a 32 and a 39. With our 4s, we have a 40, a 43, a 45, and a 47. 3, 45, 47. We have a 50, and we have a 70. Again, nothing in the 6 stem, but we leave the entire thing blank, and we include it there because it is one possible stem between 3 and 7. And so this is the stem and leaf plot that would be created from the data of animals' top speeds. Again, we need to choose the stems based on something that is pretty easily ordered because we don't want our stems to be a long, long way from each other. That would include a lot of data points in between. And also something that can group the data points into similar sets. So go ahead and see what you can do about this data set here. We're going to look at times from the women's supergiant slalom event at the 2002 Winter Olympics. Now, so these numbers are a little bit more complicated than the ones we just saw, but consider things that could be used as stems that separate the numbers from each other. Remember, we want to be able to create many different stems and not just one, but not too many, and what could be used as leaves. So go ahead and pause the video, see what you can do with this one, and then come back when you're ready. Well, with these decimal data points, since everything is in a decimal, it seems that we might be able to very easily separate these data points with stems and leaves based on what is in the whole number place of the decimal and what is in the decimal place values. So if we use those, then we only end up with 3 stems, 73, 74, and 75. And it's okay that we only end up with 3 stems here. The key is we don't want to end up with only 1 stem or with too many. If we tried to just have 7 as our stem, we had everything in 1 stem, which is not something that we want. And if we tried to include the tens digit in our stem, then we'd have to go everywhere from 738 up to 751 as our stems. And while that's not a huge number of stems, it is a lot of different stems and potentially only one leaf per stem in a lot of cases. That's not necessarily something we want either. So let's take a look at the 73s. Well, the 73s that we see 73.86, 73.95, 73.99, 73.59, and 73.64. And if we want to order these from least to greatest, we have 73.59, 73.64, 73.86, 73.95, and 73.99. Now, if we look at, let's cross those off there so that we know we've gotten to them. Now, if we look at the 74s, we have a lot of 74s. So we're going to have a lot of them to look at to try to order from least to greatest. Again, we want to order from least to greatest, partially because it will help us analyze the data and know exactly what we're looking at, but partially also because then it's easier to figure out what data points are actually represented. So we have a 7408, and we have to include the 08 because each of these leaves has two place values. 7428, 7444, 7473, 7483, 7484, 7489, and then I have 7499 sitting down here since I'm running out of space. And then finally, we're off to our two 75s, 7513 and 7517. So as a brief reminder, a stem and leaf plot is a type of data representation where we order the data from least to greatest. And we break down data into smaller points based on, in these cases, similar place values, and then we order the places that remain into leaves that branch off of the similar stems.